Hi everyone. In the previous video I discussed Ka and Kb, and the video before that I discussed Kw. Well, in this video we're going to relate all three of them to each other. What is that relationship? Let me give you that relationship right away. Ka times Kb equals Kw. Just remember that Kw is specific. Actually, all these Ks are specific for the temperature, and we'll call this, well, no. Let me put this in a box first. And then if I say, if we're at 25 degrees Celsius, maybe I should have put this one in the box actually. Ka times Kb equals Kw equals 1.0, remember the number? 10 to the negative 14. How did that happen? Before we take a look at this, let's derive it, actually. I wasn't planning on doing this, but let me derive it. So we'll call part A as the derivation. I hadn't planned on doing this, so bear with me as I try to figure this out. Okay, let's have one reaction. Let's have a weak acid. And I'll use the weak acid that we used in the previous video. HNO2. I'll just label this weak acid. HNO2 aqueous plus H2O liquid goes to H3O plus aqueous plus NO2 minus aqueous. Now, we have a Ka for this. The Ka equals concentration of H3O plus times the concentration of NO2 minus, minus in the parentheses, over concentration of HNO2. I feel like I'm painting myself into a corner. Let's keep going. Let me give you a base equation, because we're going to need a Kb. Okay, but what Kb should I use? Well, I just created a conjugate base. So why don't I use, give me 1 second, do I really want to use that? Yep, let me use that. NO2 minus aqueous plus water liquid goes to. Okay, so I'm not writing the reverse of this reaction. If I was writing the reverse, I would put NO2 minus plus H3O plus. But now I'm taking that conjugate base and I'm giving its own reaction where I reacted with water. So can you go ahead and fill in the rest of the equation just based on these two reactants? We have, oh good, HNO2, this is going to work out, plus OH minus. I'm jumping ahead. Pretty excited about this though. I haven't derived this ever, I think. This is the first time. We have a KB for that. Let me write that in, I don't know if you could tell the difference between purple and blue. KB. KB equals HNO2 times OH minus over NO2 minus. If I reverse this equation, I take the inverse of this. So, do I really want to do that? Give me 1 second. Let me think real carefully about this. No, I do not want to do that. I want to add these two equations. Okay, let's try this. So now I have equation A and equation B. What if I add equation A plus equation B? What do I get? I get, see the HNO2's cancel out. I get 2 water molecules. The NO2 cancels out. What the heck's going on here? You know what? We got it. Yeah, let's just follow this. I doubted myself. 2H2O liquid goes to H3O plus aqueous plus OH minus aqueous, and the new KB. Not the new KB, the new K. Do you remember your rules? When you add the reactions, what do you do with the Ks? You multiply them. You multiply them. But look at this. If I literally write the K expression for this, that equals the concentration of H3O plus times the concentration of OH minus. So this is KW, right? This is KW. But give me 1 second. I want to say this properly. So what did we effectively do? We effectively added the 2 reactions, and we got this third reaction. And when we add 2 reactions, what you do with the Ks, you multiply them. So now this equals Ka times Kb. This is not Kw, okay? Because Kw, remember, is autoionization. Autoionization. This is actually a new Kc, equilibrium of concentration. But what is more important is that I have this. And at 25 degrees, what do we know about this product? At 25 degrees C, this equals 1.0 times 10 to the minus 14. So that's where we're getting this equation, right there. Ka times Kb equals 1.0 times 10 to the minus 14. So, I know I put a lot of things in boxes so far, but what would I put on the equation sheet? I think I would put this on the equation sheet. Ka times Kb equals 1.0 times 10 to the minus 14, and this is my final answer. This is what I would put on the equation sheet. But again, the caveat is this is at 25 degrees C, and now we got to understand what Ka and what Kb. Look very carefully. That Ka is for this acid. This Kb is not for this acid. This Kb is for the conjugate base of this acid. So the trick is, if you're given one, you can calculate other, but you have to know for what molecule. So for instance, if given this for HA, some general acid, then you can calculate this, then calculate KB. Let me just specify. If Ka is given for this acid, HA, then you can calculate KB not for the acid. It doesn't make any sense to calculate the KB for the acid. You're calculating the KB for the conjugate base. And what is the conjugate base for HA? A minus. And literally that's what we did. See the KB of that. That is the A minus of my acid reaction. So that's the derivation. The trick is, don't get confused, because when given a Ka number, people will do 1.0 times 10 to the minus 14 divided by Ka, and they said, oh, I got the Kb. And they think it's the Kb for that compound. It's actually the Kb for the conjugate base of that compound. So in part B, we are going to practice. I have something set up for us. Let me see if I'm ready for it yet. Part B is quick practice. Calculating KB for what? Question mark. So here it is. 2 columns. If given the Ka 4. So our first example is if we're given the Ka for this acid, HC2H3O2. That's acetic acid. And the Ka is 1.8 times 10 to the minus 5. If given that, we can calculate Kb for what? What compound? Okay, do you want me to specify? I'm not going to give it the answer in this video. I'm setting it up though, the problem. For what compound? Okay? And not only that, we could also figure out the Kb. Kb equals blank. If you understood this video, I'd watch it again. If you're a little confused, watch it again and try to answer these 2 blanks. Let me give you another example. Let's take the acid H2CO3. That Ka is 4.5 times 10 to the minus 7. So you could figure out the Kb for what molecule, and when you plug in that number, what is the Kb? We could also go backwards. What about this? If given the Kb for, so now I have to give you bases. The first base is ammonia, and the Kb is 1.8 times 10 to the minus 5. If you're given a Kb for that molecule, you can calculate the Ka, but for what compound? For what compound, and what is the Ka? What is the numerical value? One last one. Let's take another base. This one's interesting. CO3 2 minus. Ooh. See, we have a carbonate up here as carbonic acid. Here we have just plain carbonate. That has a Kb of 2.1 times 10 to the minus 4. And again, what are you figuring out the Ka for? What molecule? And the Ka equals what numerical value? Okay. You want me to do one of them? Let me do this NH3. I'll do this in green. If you know the Kb for NH3, you are calculating the Ka for its conjugate acid, NH4+. And the calculation is, to get the Ka, 1 times 10 to the minus 14 divided by the Kb, 1.8 times 10 to the negative 5. 5.6 times 10 to the minus 10. 5.6 times 10 to the minus 10. That is your Ka. Okay? Let me just tell you real quick at the bottom here, trends. Very easy. Based on what we know about Ka, we know that the bigger the Ka, the more product we get, the more acidic the acid. So here's the trend. The bigger the Ka, the more acidic, the more likely the proton is going to be given up. More acidic the HA acid is. And then what about Kb? The larger the Kb, the more basic the B base is. And that's all I want to say about trends at this point. We'll get more trends in future videos, but yeah, that makes sense. The bigger the equilibrium constant, the more products we get. And so the more H3O plus we get, the more acidic the solution is. And for Kb, the bigger the Kb is, the more hydroxide we get. The more hydroxide we get, the more basic. Do you want me to put that? Because this one has a high H3O plus concentration, and if the Kb is very high here, we'll have a high OH concentration. And then you can start figuring out pHs based on those concentrations. Alright, that's all I want to do. Thanks for sticking with me while I try, I think, successfully to derive that equation right there.